Hello, and welcome to another Digital Differential Equations lecture video for Salt Lake Community College. In this video, we are going to be going through Chapter 4.4 and looking at the method of undetermined coefficients. In Chapter 4.4, we will apply the non-homogeneous principle to non-homogeneous linear second-order differential equations. We will also introduce the method of undetermined coefficients for obtaining the particular solution for a variety of non-homogeneous DEs. If inspection does not lead to a particular solution, then the method of undetermined coefficients may be the next simplest technique. To get started, let's look at some definitions. The non-homogeneous principle states that the general solution of a non-homogeneous linear differential equation of the form L of y equals f of t is the sum of your homogeneous solution plus your particular solution, where y sub h is the general solution to the homogeneous equation, and y sub p is a particular solution to the non-homogeneous equation. We will use the fact that the homogeneous solutions yh could be found using the methods that we introduced in chapters 4.1 through 4.3. Let's look at the method of undetermined coefficients. When visual inspection does not provide a particular solution yp, then the method of undetermined coefficients may be the next simplest technique. We can apply this method when the DE has constant coefficients and the forcing function f of t is one of the following. If your forcing function f of t is a constant, then probably your particular solution will be a constant also. And so we use a naught to represent a constant. If your forcing function is a polynomial of degree n, then we guess your particular solution will also be a polynomial of the same degree. It will also include all of the descending powers of t. If your forcing function is an exponential, we will guess your particular solution will also be an exponential with some other coefficient. So we'll represent a naught as my unknown coefficient. If your forcing function is a sinusoidal function, either a cosine or a sine, then your particular solution will be a linear combination of both sines and cosines. If your forcing function is the product of a polynomial times an exponential, then your particular solution will be also a product of a polynomial times an exponential, where the coefficients of your polynomial will not yet be known. And then there are several other possible combinations of forcing functions that we can use. But notice that with all of these forcing functions, there are always going to be polynomials, exponentials, or sinusoidals, or some combination of them. If your forcing function is not one of these varieties, polynomials, exponentials, sinusoidals, or some combination, then we will not be able to apply the method of undetermined coefficients. Now I put a couple of notes at the bottom. In your forcing functions listed in part 4 and 6 through 8, So this one and these ones, both terms are always included even if only one of the terms is present, meaning that even if only a cosine is present in your original forcing function, you must guess a forcing function that has both sines and cosines. We will always do that. And then lastly, if any of the terms in yp are found in yh, i.e. if one of these forcing functions is a duplication of a homogeneous solution, then we will multiply yp by t, or if necessary, t squared, to eliminate the duplication. Of course, I'd like to show you this in some examples, so let's get started right away with that. Let's look at our first example, the differential equation y double prime plus 6y prime plus 8y equals 4. In solving our differential equation, we're first going to look for your solutions to the homogeneous differential equation. So remember, when you're looking at the homogeneous DE, you literally make the right-hand side 0. Now this is where we'll be able to use the methods we developed in 4.1 through 4.3 to solve linear second-order homogeneous differential equations. For this particular DE, we'll want to use the characteristic polynomial whose coefficients are the same coefficients as that of the DE. It doesn't have to be factorable, but in this case it is factorable, and we can factor this polynomial, this quadratic, as r plus 4, r plus 2, which gives us two solutions for r and a solution for our homogeneous equation of c1e to the negative 4t plus c2e to the negative 2t. This is our homogeneous solution. Okay. Now we'll look at our non-homogeneous DE. And now this is where we want to consider, what does the form of the right-hand side of the DE look like? So we're looking here. Notice that the right-hand side is a constant. Now I'm going to look back to our table. In the scenario where the right-hand side is a constant, we're going to guess that the particular solution yp will also be a constant, but we'll say it's an unknown constant at the time. That's what A naught represents, is unknown constant. So for our non-homogeneous DE, let's guess that yp is just equal to a constant. And if this is going to be a solution, we should be able to evaluate it in the differential equation. So we'll be looking at the second derivative of a plus 6 times the first derivative of a plus 8 times a. And we want to know, will this equal 4? Now, utilizing what we know from calculus, that if a is a constant, then the first derivative of a constant is always 0. And if the first derivative of a constant is 0, then the second derivative would also have to be 0. What this leaves is a single equation with one variable, a, that we don't know. So that we can solve for a and say that a has to be 4/8, or that yp, our particular solution, has to be 1/2. Okay. Now we get to use the non-homogeneous principle to write the general solution. And it'll have to be y of t. Remember, the non-homogeneous principle says that your general solution is going to be the sum of your homogeneous solution plus your particular solution. So c1 e to the negative 4t plus c2 e to the negative 2t plus 1/2. This will be the general solution to our differential equation. If we were given an initial value problem, now we would go solve for our constants c1 and c2. I will do that in some of our future examples. However, in this example, I would like to continue with a couple other ideas that we remember. Some things I could also ask you about is, what is your transient solution? Or your steady state solution? Here you want to remember that by definition, your transient solution is a solution that decays over time. And so here we would be looking at the portion of our solution with the negative exponents. It's also your homogeneous solution in this case. So your transient solution, labeled as yt, is going to be c1 e to the negative 4t plus c2 e to the negative 2t. While your steady state solution will be the portion of the solution that remains after the transient solution has died out. That is going to come from your particular solution, yp. So here our steady state solution is just 1/2. This part of the solution, let me just type that out. This part of the solution will not change regardless if we change the initial conditions. So your steady state solution does not depend on any of your initial conditions. However, your transient solution, this part does depend on the specific initial conditions. So graphically, the way we should be thinking about this, let's draw ourselves a coordinate system. Label this your y-axis, your t-axis. Is that imagine we started with some initial condition. Y at time 0 is y naught. And we want to imagine what will solutions do over time. So in helping us analyze this, we're probably going to want to consider what is the limit as t goes to infinity of our general solution, c1e to the negative 2t, c2e to the negative 4t plus 1/2. And by definition of being a transient solution, we have the negative exponents here. Tells us these two terms will go to 0. And so our solution will always approach the steady state solution 1/2. So graphically, we see this as a horizontal line through the ty plane at the line y equals 1/2 that your solutions will approach. So if we started at any initial point y naught, our solutions will always asymptotically approach this line, where this curve is dependent on the values of c1 and c2. If I had given you a different initial condition, you would still approach that line, they still approach that steady state, but you would get a different c1 and c2 that describe that curve. So the transient solution, that depends on your initial condition, but the steady state does not. Your solutions will always approach the steady state regardless of your initial conditions. Let's look at another example. Let's find the solution to the IVP y double prime plus y prime equals 1. Now our starting point will always be to look for the homogeneous solution first. Now at this point, I'd like to pause for a moment and give you a chance to find your homogeneous solution. So if you could pause your video, work out just the homogeneous solution first, and then come back and see how we did. I'll see you in a moment. Okay, let's see how you did. When looking for your homogeneous solutions, we probably will start by writing your characteristic equation. So this would be your polynomial r squared plus r equals 0. Remember, always replace your derivative terms with r. This quadratic polynomial ends up being factorable as r times r plus 1, which gives us two roots. Either r is equal to 0 or r is equal to negative 1. This will give us our homogeneous solution as c1e to the 0t plus c2e to the negative t. However, it doesn't really make sense to leave e to the 0t. Recall e to the 0t is always 1. So we'll write our homogeneous solution as c1 plus c2 e to the negative t. This will be your homogeneous solution. Now let's go look for our our non-homogeneous solution. And when looking for your non-homogeneous solution, you always want to start by considering the form of the right-hand side of your differential equation. And here the form is a constant. And so it leads us to want to guess that yp might also be a constant. However, this is not a good guess. Recall that if your non-homogeneous guess is ever a repetition of one of your homogeneous solutions, so if this guess, or if this form, is ever a repetition of one of the parts of your homogeneous solution, we must multiply by a factor of t. Now, this is incredibly important, so I'm going to look back to our table so you can see that again. And here I'm looking at this note. If any of the terms of yp are found in yh, i.e. if they're solutions to the homogeneous equation, you must multiply yb by a factor of t, or maybe t squared if necessary to eliminate those duplications. So in this problem we're looking at, again, your homogeneous solution, a constant, is the repetition of our first part of our solution, this constant. So here we're going to have to multiply our guess by a factor of t. Now, if this is a solution, it has to satisfy the differential equation. So let's plug this proposed solution, AT, into our DE. And ask, when will this equal 1? So let's evaluate the left-hand side. The first derivative of AT is just going to be A. Of course, if the first derivative is a constant, then the second derivative will have to be 0 again. This tells us our constant A has to equal 1, and it also tells us that yp, our particular solution, remember yp looks like AT, but A is equal to 1, yp is just equal to t. With this as our particular solution, we can now write the general solution using the non-homogeneous principle as y of t c1 plus c2 e to the negative t plus t. So this again is our homogeneous solution. Plus our particular solution. Now in this problem we were given an initial value problem, so we still need to go and find out what our constants C1 and C2 are. So remember, when we're given our initial conditions, one of them is on position, one of them is on our velocity, our first derivative. So let's go find our first derivative. So now we'll have y prime of t. Now if c1 is some constant, its derivative is 0. And the derivative of c2 e to the negative t would be negative c2 e to the negative t. And the derivative of t is just 1. Now evaluating at our initial conditions, we'll have y of 0 and y prime of 0. Of course, y of 0, when you plug in 0 for t, you'll give us c1. When you plug in 0 for t, e to the negative t becomes just c2. And when you plug in 0 for t, this last term becomes 0. Our derivative. When you plug in 0 for your derivative, I think we get just negative c2 plus 1. And from our initial conditions, we know y of 0 has to be 0.1, and y of prime of 0 has to equal to 0. This leads to c2 equals, I think this is negative 1 or positive 1. This is c2 gives c2 as a positive 1. But if c2 is positive 1, then we have c1 plus 1 has to equal to 0.1. So that c1 has to be, if I subtract 1 from both sides, I think that's negative 0.9. Which gives the solution to our IVP as y of t negative 0.9 plus e to the negative t plus t. This is the solution to our initial value problem. Again, I think it's important for us to think about these graphically as well. What do these solutions actually look like? So here you might want to consider drawing your solution curve. Here we started with an initial condition of, well, what was our initial condition? It was 0.1. So here we had y of 0 is 0.1. And I want to consider for this solution, what is the limit as t goes to infinity? Remember that the limit of the sum of a bunch of functions is the sum of the limits. So here we can evaluate each one individually. And notice as t goes to infinity, e to the negative t would have to go to 0. As t goes to infinity, t goes to infinity again. So you'll have negative 0.9 plus infinity. This goes off to infinity, which tells us our solution curve would start here and have to kind of go off towards infinity. That's the solution to our IVP. Okay, let's look at another example. Now I want to change our example up a little bit to look at different kinds of forcing functions. So in this example, let's consider the IVP given here. Notice the exponential forcing function on the right-hand side. Now again, with our problems, we always must start with the homogeneous solution, so we know that there's a repetition in our solutions. So our homogeneous DE will look like y double prime minus y prime minus 2y equals 0. Which you're probably jumping right to your characteristic equation. Notice that our characteristic equation is factorable as r minus 2, r plus 1 is equal to 0, which gives us two distinct roots to our characteristic equation. R is equal to 2 or r is equal to negative 1. And I'd like to give you caution here. A lot of students make a simple algebraic error by forgetting to change their sign. Be careful of that here so you don't have just simple errors. Okay. This gives us our homogeneous solution as C1e to the 2t plus C2e to the negative t. Which is your homogeneous solution. Do not solve for your constants now. You have to solve for your constants at the end of the problem. So now let's proceed and let's go look for the non-homogeneous solution. For our non-homogeneous solution, again, we want to look at the form of our forcing function. So notice that our forcing function is an exponential function. So if you look at our table, it says that if we have an exponential forcing function, then our guess for yp is still going to be an exponential forcing function, but it'll have an unknown coefficient. So we're going to replace this with an a as our coefficient. The exponent part will still stay the same. So it'll be e to the negative 3t. So we're just making an unknown coefficient in our guess, but the rest of the forcing function stays the same. Now, if this is going to be a solution, it has to satisfy the DE. So let's evaluate our DE with this proposed solution. So AE to the negative 3t, second derivative of that, minus the first derivative of AE to the negative 3t, minus 2 times our guess, and somehow we want this to all equal 2e to the negative 3t. And our job is to figure out what value of a makes this equation valid. So to evaluate this, I'm always going to work on this from right to left. And I do this because of the way I take derivatives. So the first one, the first parenthesis term here is no derivative. That stays the same. So I'll just write this as negative 2 times AE to the negative 3t. Move to your middle term. We'll take a first derivative. Because of how we take derivatives of exponentials, the derivative of AE to the negative 3t is going to be negative 3a e to the negative 3t. And if that's your first derivative, then your second derivative is just the derivative of that. And that should be positive 9a e to the negative 3t. Now notice the left-hand side are a bunch of terms that look like some constant version of a e to the negative 3t. These are all similar terms, and so if we try and combine our similar terms, we have 9a to the 3t. This will be a plus 3 more a e to the negative 3t's minus 2a e to the negative 3t. I think this is going to be 9 plus 3 is 12. 12 minus 2, I think this is going to be 10. A e to the negative 3t. And this all has to equal 2e to the negative 3t. Notice this leads to 10a has to equal to 2, or a has to equal to 1/5. This is our coefficient, our constant a in our guess for yp, which means yp has to be 1/5 e to the negative 3t. This is what yp has to look like with our specific coefficient that we found. Now we can write our general solution by the non-homogeneous principle as y of t equals c1e to the 2t plus c2 e to the negative t plus our particular solution 1/5 e to the negative 3t. This is going to be our general solution. Now remember though, we were given an initial value problem in this time. So now we have to go figure out what our constants are. So let's start by finding our derivative. And the derivative of c1e to the 2t is 2c1e to the 2t minus c2e to the negative t minus 3/5 e to the negative 3t. Our initial conditions are at time 0, so let's evaluate both of these at time 0. When you evaluate your position function at 0, I think you get c1 plus c2 plus 1/5. From our initial conditions, we know this has to equal 1. When you evaluate your derivative, we should have 2c1 minus c2 minus 3/5. And from our initial conditions, we know this has to be 0. This gives us our system of two equations with two unknowns. There's lots of ways you can solve this, but I want to set this up to be able to use the elimination method. So I'm going to get just the C1 and C2 on the left-hand side. Let's move these constants, the 1/5 to the right-hand side and the 3/5 to the right-hand side. I think that gives us C1 plus C2 is 4/5. 2c1 minus c2 is 3/5. Now, by the elimination method, if we were to add these two equations together, the c2's being opposite in sign would cancel. And I think we get 3c1 equals, I think that's going to be 7/5. Which tells us C1 would have to be 7/15. Okay, now if C1 is 7/15, though, then I'm going to grab our first equation we have here. And if C1 is 7/15, I think this means 7/15 plus C2 has to equal 4/5. I'm going to grab my calculator for this. Look at 4/5 minus 7/15. So 4/5 minus 7/15. I want my answer as a decimal or as a fraction, though, so I'm going to hit the math button and choose option 1 for fraction, which tells us it should be, I think that says 1/3. Now that we have our two constants, we have everything we need to write the solution to our initial value problem. As y of t 7/15 e to the negative 2t plus 1/3 e to the negative t plus your 1/5 e to the negative 3t. And this is now going to be the solution to our initial value problem. Okay, let's look at my follow-up question, the next question that comes after this. Here we're being asked to find the general solution to the given initial value problem. And what you should notice with this is that the left-hand side of our DE is the same. I'm just changing our forcing function. In our previous example, our forcing function was 2e to the negative 3t. Now we have a different forcing function. So let's start with our homogeneous differential equation, which looks like y double prime minus y prime minus 2y equals 0. And because this is the same homogeneous equation we looked at in our previous example, we already know that YH has to look like C1 e to the 2t plus C2 e to the negative t. This is our homogeneous solution. Now the non-homogeneous solution. We think about what our guess for yp should look like. And when thinking about your guess for yp, again, you always want to focus on what is the form of your forcing function. And here our form looks like an exponential, so we'd like to guess, again, an exponential. So I think our first guess should look like a e to the 2t. However, what you really have to focus on with these problems is to notice that this forcing function is a repetition of your first homogeneous solution, meaning that this equals 0 when you evaluate your dE. It's never going to equal 5e to the 2t. That's what it means to be a homogeneous solution. Again, just to emphasize this, if you were to look at e to the, well, let's put an a here. A e to the 2t, second derivative of that, minus the first derivative of a e to the 2t, minus 2 times a e to the 2t. This will equal 0 by definition because a e to the 2t is a homogeneous solution. So hence, again, it will never equal to 5e to the 2t. So whenever, again, we have a repetition of a homogeneous solution, you always must multiply by that factor of t. So we're going to guess at e to the 2t. Now this time I'm going to do my algebra a little bit differently. I'm going to go ahead and find my derivatives now. We know we're going to be substituting this in for y double prime and y prime. So let's just go find our derivatives now. So let's look for yp prime. Now when looking at yp, remember that yp, our guess, is a product. At times e to the 2t. So because this is a product, we have to use the product rule. So the derivative of the first is going to be a times the second regular, plus by the product rule, the derivative of the second. The derivative of e to the 2t is e to the 2t, times by the chain rule, the derivative of the 2t, which goes in front, to give us 2at e to the 2t. If that's our first derivative, then our second derivative, now the derivative of a e to the 2t would be 2a e to the 2t. And on our second term, again, notice that we still have a product here. So product rule still applies. The derivative of 2at is going to be 2a times the second regular, plus by the product rule, the derivative of the second, be e to the 2t times by the chain rule of 2. I think so it'll make this a 4at e to the 2t, which I'd like to combine similar terms here and call this 4a e to the 2t plus 4at e to the 2t. So now if we evaluate these in our dE, again, we're supposed to have our second derivative, which we have here. I'm going to put these in grouping symbols just to make sure we can identify which part is which. So 4a e to the 2t, 4at e to the 2t, that's our second derivative. minus our first derivative, which would be ae to the 2t plus 2at e to the 2t and it'd be minus 2 times our original function, so minus 2y, which is at e to the 2t. And again, somehow this all has to equal to 5e to the 2t. And it should for the appropriate choice of a. So now let's look at combining some like terms. First, I'll grab the terms that don't have a factor of t, which is this one and this one. And combining those two terms together, I think we get 3ae to the 2t. Now we'll look at the ones that have a factor of t. So this 4at e to the 2t. Don't forget to distribute this minus. This would be another minus 2at e to the 2t. And here's another minus 2a e to the 2t. So I think you have 4 minus 2 minus 2. I think these all cancel. This leads us to 3ae to the 2t has to equal to 5e to the 2t, or that 3a has to equal 5, which tells us a has to be 5/3, or yp is going to be 5/3 t, don't forget that factor of t, e to the 2t. This is our particular solution to the non-homogeneous equation. Now we'll be able to write our general solution by the non-homogeneous principle as C1 e to the 2t plus C2 e to the negative t plus 5/3 t e to the 2t. This is our general solution. If we were given an IVP, now we would move on and look for our constants C1 and C2. But I'm going to stop this part of the example here because I think it's sufficient. And I would like to lead you with a note of encouragement. Please, I'm emphasizing in capitals here, look at example number 9 on page 251 of our textbook. At the example referred to as the serpent bites twice. I think this is a great example that you need to see for how you may need to manipulate your guess for YP by multiplying by this factor of t like we did here. So definitely look at this example, the serpent bites twice. This is an important example. I'm just choosing not to work this example out in our guided notes, but this is an important example that you need to see. Okay. Now, I'm going to stop this video here since we're at 55 minutes now, but I'd like to do, I think there's 3 or 4 more examples in our guided notes still. So I want to create another video to look at those additional examples. I hope this is helpful, and I'll see you in our next video.